Hey everybody, and welcome to this video in which I'm basically essentially going to be kind of talking about some of the basics of the rectangular coordinate system and some of the metrics that we use when we, examine graphs or look at the dimensions of some maybe geometric figure that we plot in the XY coordinate plane. But let's go and get started and just review a few things, such as we have a horizontal number line we refer to as the x-axis, and the y-axis, of course, is our vertical number line. And we tend to refer to these four areas as quadrants. I just want to make sure that everybody's on the same page here, but we have quadrant 1, quadrant 2, and it does go in counterclockwise order. But quadrant 3 and of course quadrant 4. Thing to keep in mind here is that you don't have to use Roman numerals, but that's typically the convention. And also that we end up typically plotting what we honestly almost all the time call solution points, but because we're referring to algebraic expressions, but these coordinate pairs in which we always deal with the x value first and the y value, of course, second. Now, if you want to be really nerdy about it, as a matter of fact, this x value here, this first value, is known as the ordinate, I believe, and the second value is known as the abscissa, and that's it's not necessary knowledge, but hey, who knows? You might need to know that someday. But anyways, let's take a look at graphing a few points here. How about we start with the negative value, negative 2, 1, and we'll deal with this point here. How about 3, 4? Okay. So essentially, just recall that with the x value coming first, we'll start at this point 0, 0. We refer to the as origin and as the origin, and proceed in whichever direction basically this orientation denotes. So we say negative 2, we'll go left 2, left 2, and since this is a positive 1, we'll go up 1. But really, basically what I want to point out here is it's going to be a long year, and I appreciate when people label points, and also that what we're really looking at here is a directed distance, okay, from the y-axis on the x-axis of a negative distance of negative 2, and a directed distance, a y distance of positive 1. So this is essentially why we refer to this as the rectangular coordinate system, of course. Just going over some of the basics, but let me undo a few strokes here. We say, okay, so negative 2, 1, we'll graph this point here, 3, 4, just to make sure everybody's on the same page. So over 3, up 4. It's not that I'm worried about actually graphing points. The one thing I do want people to keep in mind, essentially, though, is this. When we're up here in quadrant 1, we're dealing with two positive coordinate values, but when we're over here, we're dealing with a negative and a positive. And I know, I bring this up, and I don't know what courses people are taking as they tune into this video. I know my students are taking pre-calc, but anyways, this comes in handy later when we deal with some trigonometry. So anyways, this idea of plotting points to the rectangular coordinate system, very, very straightforward. Really, what I want to get on about, though, is this. We are going to be dealing with a lot of graph theory in which we kind of explore a graph as representing, say, a variable relationship, perhaps between distance and time. Or maybe we are using the coordinate plane because it is easy to measure, to say, as a metric tool to measure geometric solids, okay? So, it's very important for us to know how to calculate a few things when it comes to, points in the coordinate plane. And those two things we're going to be dealing with today happen to be the distance between 2 points and as well as maybe the midpoint between 2 points in this video, okay? So we're going to start with this idea of distance, okay? So let's take a look at these 2 points here. We'll switch out this color here. I think we'll go over to, how about, like a magenta. But anyway, I think that should work. Oh, there we go. Yeah, that'll work. Anyways, so I'm going to color these in a little bit more. But let's say we did want to find the distance between these 2 points here, okay? So I'm going to go ahead and draw on this little segment here that connects the two, and we can call this distance. How about, for the sake of convenience, you can see where I'm going with this, we'll call this C. Okay, so anyways, this value C, go back to white here, this value C is the distance that we're trying to figure out. Let's take a look at this and say, how could we find the distance between these 2 points? And see, here's where the kind of the convenience of the rectangular system comes into play. If you think back to geometry, and I called this C for a reason here, what we can do is we could necessarily kind of imagine here that this is necessarily a right triangle. And the neat thing about this right triangle is, 1, we can use the Pythagorean Theorem to solve for this value C, but 2, we can do this because we actually know the sides of this triangle here, okay? So this y distance here, you can think of this y distance as kind of essentially the difference between the y value of, say, the second point and the y value of the first point. That is, if this is at a height of 4 and this is a height of 3, we can 1, we can necessarily say the total distance is 3, But really what I'd like to kind of point out here is that it's this distance 4 minus 1. And same thing with respect to the x-axis, but let's take the x value of the second point. We typically do the second point minus the x value of the first point. We say this would be the distance 4 minus negative 2, which, of course, your algebra would say is plus a positive. Now, to kind of, explicitly point this out, we say this would necessarily equal here 3, this distance 3. Oops, we're using brackets here. And this would equal, of course, this distance 6. But the important thing here is this. We now have this triangle. If we kind of imagine this down here now, we've got this triangle in which we can determine this is 3 and this is 6. We can go back and look for c. So kind of a recap here of the Pythagorean, of course. A squared plus b squared is c squared. But in this case, we have the two legs, a and b. We say is 6 squared and 3 squared. And I know this is pretty trivial and elementary stuff, but I always ask my students that if they're going to be plugging in numbers for values, the best thing you can do for yourself is actually put in these parentheses where the variable value was before you put in the number. It kind of helps you later with negatives. But we say, okay, so here's what we've got. We've got 36 plus 9 is equal to c. Of course, 36 plus 9 is 45 is c squared, pardon me. And you know what? To solve for c, we'll take square root of both sides. And you're simply left with this. Square root of 45, which of course is the square root of 9 times 5, and we know the square root of 9 is 3. So we say this is equal to technically plus or minus 3 radical 5. Now I want to make a comment on this plus or minus. It is technically correct, however, in this case we're speaking of geometric distance. What we're going to do is we're going to disregard the negative, okay? So if I kind of go back and erase that here, we say positive 3 radical 5 is this distance c, okay? So we say 3 radical 5. Okay, so this is no new news. What I wanted to get on about is essentially this idea of the distance formula, okay? So we're going to look at this problem again and kind of modify it a little bit. But let's say we had, in general, 2 points. We're going to label these. We'll call this x1, the x value of the first point, and y1. And we say, okay, we'll call this x2 and y2. Essentially, we're going to set this problem up the same way. And we can even call this distance c again. Okay, how about we do this here? We say, whoops, there we go. This distance c. We can even look at it this way, okay? Now remember, in the first time we looked at this problem over here on the left, we said, okay, what we need to find here is the y distance and the x distance. We can necessarily use those to use the Pythagorean theorem to solve for c. So when we found the y distance, what we really did was we found the difference between the two y values. So now this time, instead of writing the y value of the second point, the y value of the first point, we'll write it quite generally like this. So we're going to call these distances this. And you know what? In some texts, you'll see these referred to as delta x and delta y. I don't want you to get tripped up on this if you don't have to, but we refer to this Greek letter delta in the sense of difference. We use the Greek letter delta as shorthand for the difference between the two y values. But looking at it this way, what we can do is we can necessarily set this up as a Pythagorean situation again. So how about we pull out maybe like a lighter blue here. If I can get this to work, there we go. But we say up here in this sense, we say, okay, so how about we refer to this? This distance in the x direction, we would say, okay, is x2 minus x1. And we would say that side length squared plus, now the distance in the y direction, y2 minus y1. That side length squared, that should, in a Pythagorean sense, add up to the third side squared. And, since we're necessarily looking for this distance right here, let's go ahead and solve for it by taking the root of both sides. And essentially what we're doing, of course, this is the fun distance formula that I always love to write out. I usually use deltas, but just for you guys, I'll use the longhand notation. You might be thinking, longhand? Yes, longhand. Anyways, okay, so we say this value c, I'm going to temporarily change the letter here to this. And maybe you can kind of infer why, but we're going to refer to this as the distance formula. Okay, so this distance formula, first things first, if you're taking notes on this bad boy, you want to pause the video at this point, and you want to write this down. Now, the proof's always nice, or the demonstration, the illustration of the property, which is right here, is nice. But essentially what you want is this formula right here, because what it allows us to do is essentially the same thing we did over here on the left, but in a little bit quicker fashion. So here's what I'm going to do here. We're going to go ahead and open up a new one here, and